So this also confirms all this picture. And now let's come back to cross-section of a plus and minus annihilation. Of course, if you are interested in specific final states of hadrons, we need to consider everything, the first phase and the second phase. So this fragmentation. If you are interested, for instance, in production of 3 pions and say 2 and proton antiproton, then we need to consider all the things. However, if you are interested in total cross-section, for this, it's enough to compute only this. Right? For total cross-section, because we are not interested what happens after this. So we produce quark and anti-quark, and we are not interested how they will further develop.
I see.
Clear? So to say, you can consider the process again as a describe probability as a product of probability of this process and then fragmentation. And then when you sum up over all possible final states of hadrons, that will give you 1, right? So then eventually the probability is determined by the probability of this initial phase production of quark and anti-quark. Clear? This is important. So therefore the total cross-section of E plus, E minus into hadrons is given approximately as the sum over all possible quarks of cross-section of E plus, E minus into quark and anti-quark. I'm writing approximate because we will study as the lowest order process. But you also need to take into account cross-section and also a possibility of emission of hard gluons. So that we will discuss a little bit later. So in the first approximation, this is correct. And so you need to sum over all possible quarks or quark-anti-quark pairs which can be produced in this process. So let us compute this individual cross-section. It is convenient to compare this cross-section with production of mu plus, mu minus pair. And actually experimentalists are doing normalization of hadronic processes to mu plus, mu minus. It's convenient because you can eliminate many uncertainties. So let us compare this with the process of E plus, E minus annihilation into mu plus and mu minus. Here there is no strong interactions, so everything can be well computed and studied. It's very convenient actually process for experimentalists. The diagram is similar, and in final state we have mu plus, mu minus. Here's plus and minus with a photon. Cross-section of this process can be actually restored using again dimensional arguments. So it's clear that it should be proportional to alpha square, because we have E here and electric charge here, then we square this when we compute probability of cross-section. So you have also alpha square. And then just on dimensional ground, at high energies, masses of these particles are not relevant. The only parameter which we have at hand is the total energy in the center of mass. Center of mass system, right? So if you neglect masses of the particles, so this is the only what we have. And to have a dimension, here is centimeter square, this is S, is total energy in the center of mass square, right? So it's 1 square, right? And then it's additional factors here, 4 pi over 3. So if you make exact computations in the lowest order perturbation theory, you will get this result. So this is for mu plus, mu minus. Now for the quarks we have the same diagram, and the only difference is the electric charge, right? Here we have muon electric charge is 1. For quarks we need to put here electric charge of quark. Okay? So that for a cross-section of production of a given type of the quark, so let me put I index here. We will write the same expression, 4 pi alpha square 3s multiplied by qi squared, and this is electric charge of a given quark in the units of just electric charge of muon. Okay, so for instance for U quark Q is 2/3 and for D quark it's minus 1/3. So then the total cross section into hadrons will be given by the sum of this sigma, right? So my best is write immediately. Sorry, let me write the following first. So I will write immediately the ratio of the sum over cross sections into hadrons over the sigma into mu plus mu minus. Okay, so it's qi. So this is what I will introduce, the ratio of total cross-section into hadrons over cross-section into mu plus mu minus, and clearly this is just given by q I square and I, right? Because these common factors cancel, and I will have such an expression. For the ratio, so this is the definition of total cross-section into hadrons over cross-section into mu plus mu minus pair. Correct? And our experimentalists measured this ratio. So let me present the experimental result. Ratio as the function of energy square root of S, and that is measured this in GeVs. So let us consider first the region below 3 GeVs. So we need to count which type of the consider which type of the quarks can be produced in this region. So we can produce U bar, right? We can also produce D and D bar, and strange quarks, right? S and S bar. So these pairs can be produced in this region. But we cannot produce charm, for instance, because charm, you need to produce 2 charm anti-charm quark, and that requires energy about 3 GeV. So this is why I put here the scale. So now let us use this formula and count what is this sum of the charges, and sum of qi squared is what? So we have 4 over 9 plus 1 over 9 plus 1 over 9, right? So this is from U quarks, this is from D quark, and this is from strange quark. And so what we will get here is 6 over 9, which is 2 over 3, right? So what experimentalists are measuring, so what is the result if someone see what is this? So what they measure is actually not this, they measure 2. And this is precisely because there are 3 colors, and all these quarks are present in 3 colors, and then you need to multiply by 3. So this is a big difference. Is it kind of convincing that you have really 3 colors, that quarks are really in 3 colors, not in 4 and not in 2? So the accuracy is now extremely good. So it's 2 with very small error bars. Now, when you go to higher energy range, above 3 GeVs, you need to add charm and anti-charm, which means that you need to add here again 4/9 and then multiply by 3, and you can obtain that here it should be 3 1/3. You can count and check. So here is the resonance region. Here you have something like this because of presence of resonances. But then it's 3 1/3. Now above 10 GeVs. Above 10 GeVs you have production also B and B bar. And we need to add their electric charges, and what you will get is 3 2/3. Here the jump is small, and again there's some resonance here related to epsilon production. So this is overall picture. So what is next? So if you start to further increase the energy, by the way, that has been measured at slug, and then also in this. So if you start to increase further, square root of S, what you would expect? Tell me. Top quark. So before top quark, there are some other events actually. Top quark is very heavy, and before that, what is important that Z boson start to contribute to also to this production. But we will stop at this point. So if you go further, then it will be a different change because it will have contribution from Z0 boson, which actually also mediates all these processes. Since I have not introduced coupling constants, I will stop at this point. Okay? I hope you agree that color exists. And then we have this exercise with tau lepton decay, where you also need to take into account 3 colors. And so the measurements of tau lepton decay, which has been done later than this. So this is one of the first experiments which confirms existence of color. So that also confirmation, and there are many other confirmations of existence of color. Now let.
So we include this tau lepton here in this.
Why? So we are studying annihilation into hadrons, and just for convenience, we kind of computed the ratio.
Okay.
Because they have the same 4 channel. You can do this also for tau lepton if you want, but at higher energies, because tau has a bigger energy, right? So tau started to be produced somewhere here, 3.6 now. Now, mu plus mu minus is very convenient, and actually all these experiments, they also have these decay channels. From experimental point of view, they measure annihilation into hadrons and into mu plus mu minus in the same experiment. And then they just produce the ratio, which excludes many systematic error, everything, so experimental features. It's very clean experiment. Now let me discuss discovery of gluons. So color is still just color, right? It's a degree of freedom. But then we introduced dynamics related to this degree of freedom, saying that color is actually not just for classification of particles or labeling, but that also has dynamical characteristic. This is coupling constant of quarks with gluons, new gauge bosons. So let me now discuss discovery of gluon. There are a few steps in this discovery. And first is just measurements of total momentum which quarks carry inside the hadrons. Remember, we introduced number density of quarks right? And actually there are different types of the quarks we can introduce, and let me denote this by the same number. So this is for U quark. Then we can introduce this number density for D quark, then for strange quark, and whatever it is. So actually even B quarks are present, or charm quarks inside the proton. But the density is very small, so you can produce virtually this heavy quarks. So X is a fraction of total momentum of nucleon, proton, or neutron, which is carried by a quarks of given type. So therefore, total momentum is given by Pn, and then we need to integrate over x and n, x. Okay? So remember that this is fraction, x. Fraction multiplied by momentum of nucleon, so this is momentum of nucleon. So Pn multiplied by x is the momentum of a given parton. Okay? Then we multiply by number density and integrate over the x. So this is total momentum of which actually carried by the quarks of a given type n. And so we have u, d here, s, etc. Okay, so here n is u, d, s. And so you need eventually, you can sum over all types of the quarks. So you can do the following. Here is p total quarks, and this is given by this p, n, and n. Okay, so in this way you can compute total momentum which is carried by quarks in proton or in neutron. So what you would expect? What is this? Remember that total momentum of nucleon is Pn, and then we compute amount of momentum which is carried by quarks. And you can test this by studying electromagnetic interactions.
It will be less than Pn probably.
Yeah, so what they have found, it's even less than half of Pn, which means that the quarks actually carrying not whole the momentum of nucleon, but only part of the momentum, which means that inside the nucleon you have another carriers. So another component exists, which you cannot probe in electromagnetic interaction, which means that this is neutral component, which also carries, so there are partons which are neutral, which you cannot probe by electromagnetic interactions, and also weak interactions, but they carry momentum, even more than half of the momentum of the nucleon. And of course the idea is immediately that it's probably the rest is due to gluons, right? So. Which means that momentum in gluons is even more than 1/2 of momentum of nucleon. And actually this fraction increases when you probe nucleon at higher and higher energies. So this is one indication. The second indication is violation of scaling. So remember, scaling means that this n, which is essentially structure function, which we have introduced before, the structure function which is proportional to nx. In the case of scaling, depends only on x. But what has been realized that eventually this n depends not only on x, but also on q squared. Momentum transfer. So momentum is not a charge, but this is what is used. So q squared is defined as q small square moduli, because this is negative for teaching and exchange. So interesting thing that, you change microscope and you see different distribution of quarks. So how it can happen that the structure of the quarks, or this distribution of quarks, or number density of quarks or particles of a given type changes with the strength of your microscope. And the changes are of quite definite form. So if you show this structure function nx multiplied by x as a function of x, and we had something like this at certain energy. But then when energy increases, what happened is that this part, the valence quarks, decreases, and here is increasing part. So evolution is like this. So this is for higher and higher energy. So let me put here E1, this is E2, and this is E3, and evolution that this E1 is smaller than E2 and smaller than E3. So what happens is that this part becomes a bit suppressed, and here the soft particles part increases. So there is nice interpretation of this fact. Again, you can use optics if you want. This is the same physics. So when you have bad resolution microscope, you see your partner walk. Okay? But when you have better microscope, you see that this is not just one particle, but it actually is something of this type, for instance. Or something like even more if you increase the resolution. So you will see that it's even something like this. So if you look from far, in bad resolution, that looks like a single structure. But in details, you see actually that's more complicated stuff. And of course here, so here you have X, for instance, this quark has particle has fraction X. Then here, because you emit gluon, the quark already has X prime, which is smaller than X. And this why, with increase of Q square, and this is equivalent to increase the resolution, you see more soft quarks here, and you see less partons with a big fraction. Also because you have more and more gluons, right, in this picture. Clear? Just like, if you look for big distance and you see there's a person is going, but then you approach closer, you see that person is bringing some child with him, right? It's kind of very classical feature. Okay? So that actually explains violation of scaling. To explain this, you need to introduce gluons and interaction of quarks with gluons. By the way, it was some question how we actually know that these are quarks and the quarks with a given characteristic. This has been, let me kind of make one deviation from this. I will continue with discovery of gluons. So what happened actually, people measured this deep and elastic scattering on protons, actually hydrogen, on deuterons, which is composed of proton and neutron, and on some other quarks, nuclei. Not only this, so that was electromagnetic interaction, but also weak interactions were used to study structure of nucleons. Neutrinos were scattered also. So you see here the quark content is different, right? So if you just focus on valence quarks, here we have what? We have two U quarks. So it's like this. We take this number density and one D quark, right? So this is the quark content. In deuteron, you have symmetric situation. You have the same number because you have proton and neutron, and here you have the same number of U quark and D quark. So you have 3UX plus 3DX. In neutron, you have opposite situation, right? So you have two D quarks and one U quark. And when you sum up, the combination which you probe is this one. Bottom line, and you see these are independent combinations. So studying or measuring deep and elastic on hydrogen and on deuteron, you can extract independently the distribution of U quark and D quark. And also check that everything is okay, that electric charges are assigned in correct way. And you can also other nuclei, which give you another combinations. So not only this, as I said, you can use weak interactions. And so what has been studied, for instance, muon scattering, muon neutrino scattering with emission of muon. So this scattering occurs on what? It occurs on D quarks, which are transformed to U quark, and not on U quark. So in this scattering, you are probing immediately distribution of D quarks. So making all these measurements, you actually can extract what are different distributions or densities of different quarks, and also check that you assign correct electric charges. For instance, here, scattering depends not on electric charge, on G Fermi, remember? So in this way, you can check also what are electric charges you need to ascribe to this U and D partons. And so in this way, eventually, it was identification of partons with quarks. Of course, this is not one-day check, so it took some years to make all these measurements and to check that all the picture is correct. Okay? Now discovery of gluons. So this is another hint, but not yet discovery. And discovery of gluons is based on the fact that you can produce jets associated with gluons. Again, let us consider E plus and minus annihilation. And you have quark and anti-quark. But then you can emit also gluon. It's like a Bremsstrahlung. It's analogy of the process of emission of gamma. So gluon can be emitted from this line or from this line. Yeah? So you have two diagrams for this type. So the process is that you have E plus, E minus, go to quark, anti-quark, and gluon. So, and you expect actually that you have fragmentation not only quark and anti-quark, but also fragmentation of this gluon. And so you expect 3 jets which correspond to these particles. The process was not immediate, and the experiments were at Decay. It's in Germany. And the first, so they had E plus, E minus collider with the name Petra. And the first hints that you have a process of this type has been obtained in 1979. So they have detector with the name Tasso. And what this Tasso detector observed, they observed widening of one of the jets. I will show you the slides with these jets. You'll see how it looks like. So you have collision. You have in final state 2 jets. But in some events, one of the jets becomes wider than another one. And so interpretation is that you have quark-anti-quark production, and then one of the quarks producing gluon. And this widening is associated to production of gluon. So for instance, this is quark, and this is due to quark plus gluon. And at lower energies, you cannot resolve these 2 jets produced by gluon and quark. So let me write also that this vertex has the QCD coupling. I will have. And at large energies that become small, you can really treat this in a perturbative way. Well, eventually, in 1984, another experiment, Jade, also operated in Decay, has observed 3 jet events. It look like you have this E plus, E minus annihilation line. You have 1 jet. You have another jet, and the third one. So that the event looked like this. So this jet with smaller number of particles and lower energies has been associated with jet due to gluon. So that's 1, it's E2. And the hierarchy was that E1 is bigger than E2, and this is bigger than E3, and the sum of energies in these 2 jets was approximately the same as the energy of this jet. So it's clear that something shared these 2 energies. So the interpretation was that you are producing here the gluon. So not only this, you measured here the angle or angular distribution between the direction of this E1. So this is direction of production of initial quark-anti-quark pair, and the third gluonic jet. And the distribution, so phi distribution of events, depends on the spin of gluon. And what has been found that the angular distribution is consistent with the spin 1, as it was expected. This is gauge particle. So you see not only presence of gluon, but also measurement of the spin of this particle became possible. So are you convinced that all this picture is correct? You see, I'm just giving one line, but at each phase, at each experiment, people ask question, are we understanding this correctly? If there are some other interpretations, some other possibilities. This has been explored. And then what has been shown that other possibilities are irrelevant, so they do not work.
These results also confirm that the gluon couples to itself?
To couples to?
To themselves.
Not this one.
But then how can you produce a jet if gluons?
Well, that's already more complicated. So here we see just 3 jets. And so here you have eventually production of fragmentation into hadrons. It's not immediate.
Yeah. But as you explained, the fragmentation before is because quark and antiquark are interacting, and then this intermediate gluon breaks and creates pair.
Well, you may have here emission of gluon and say something like this, and then it actually decays into 2 gluons, and that forms some hadron. It's not immediate. Of course, everything should be included, but that's already kind of next phase when you have formation of hadrons. So that determines how this. Here you have which kind of the hadrons you are producing in these jets. And of course, in this way, you can also measure this coupling J, right? You can measure J, QCD. Just comparing number of events with just 2 jets at lower energies, so 2 jets, because at any energies you have 2 jet events, 3 jet events, and then eventually when 4 and 5 jet events have been found, which actually corresponds to production of more gluons. You may have emission of gluon here. And so the number of 2 jet events, number of 3 jet events, number of 4 jet events has been measured, and in this way you can confirm what is the size of the gauge of this gauge coupling. Okay?
How is the angular distribution related to spin?
Well, that you need to, you have angular momentum constant. You have quark, right? And so the quark is then producing prime and gluon. So you need to consider this process. And for instance, you need to satisfy, so you have quark with a spin, for instance, directed in this way. And then you have in final state, say spin in this way, and then gluon. So for instance, you will have no, if the spin is 1, the process when gluon is moving in the same direction. I'm giving just idea where sensitivity is. Okay, because here you have spin 1/2, and here you'll have 3/2 spin. So which means that this direction is forbidden. You will have more events. So you will have no events when spin is in this way, and the more you have the spin in this way. So of course, if you flip the spin here, then you might have a gluon directed in such a way. So there is no such a situation if spin is 0. You will have more isotropic distribution. But one needs to do computation. So this is just simple angular momentum conservation, which allows you to see where the dependence appears, how it appears. For scalar, usually you have isotropic because you can emit this in any direction. For spin 1, you need to sum the spins in final state. Okay. So we change the topic and now we move to resonances. And we'll now discuss dynamics of resonances. We already discussed this because essentially this epsilon or J psi, these are resonances, what we call resonances. And now I will say more about this. And then we will briefly discuss W boson discovery. And you have exercise actually. Sure. So practically all the particles are unstable. Most of the particles are unstable. So what are stable particles? Massless particles are stable. Photon is stable. Right? Gluon is stable. Then particles with masses still can be stable. And a few of these particles exist, but for that stability one needs really to have a good reason. So, for instance, electron is stable because of electric charge conservation. Well, it may not be exact, so people are still measuring possible decay of electron, for instance, into neutrino and gamma, and put the upper bound on this on the rate of such a decay. And so, or put lower bound on lifetime of electron. Then proton, probably stable, because of baryon, a good baryon number, if it is good, right? So baryon number. This would actually ensure stability. But baryon number can be broken, and it's broken even in standard model at non-perturbative level. So that's probably tells you that at some level proton may be unstable. Now neutrinos.
In what process is broken? The baryon number?
Sorry?
Could you give an
Actually, I mentioned already. So proton can, for instance, decay into E plus and pi zero. This is kind of classical process.
Oh yes, but it has never been discovered.
Yes, that's what I'm saying. So still people are looking for.
Okay.
And this is one of the main goals of hyper-Kamiakande experiment. This is bigger version of super Kamiakande to search for this time of the decay. So that will improve maybe by 1 order of magnitude lifetime. That's actually a discovery of this that will be really greatest discovery, one of the greatest discoveries. Also indicating that there is some new physics, say, below Planck scale. Now, neutrinos are at least the lightest of 3 neutrinos, which we know is probably stable. And this is because of angular momentum conservation. Neutrino has spin 1/2, and we do not know particles which are lighter than neutrinos and have semi-integer spin. So the rest of the particles are decaying, some quite fast, and those who decay very fast we call resonances. Actually muon decay, but we do not call muon that it is resonance. The lifetime is quite big, and so in many respects it just can be considered as a really particle on the mass shell which is propagating. The particles like these hadrons, for pion also we do not consider the pion is the resonance. Also in principle this is the resonance. All decaying particles can be treated as the resonances. So usually we are calling the resonances when the width of the decay is somehow comparable with the mass of the particle. But we will specify this later. So let me give first a phenomenological description of resonances. We have already introduced the law of decay. So if we have n particles, then the change of number of particles with time, and if the particles are decaying, is described by this law, and gamma is called decay rate. Right, so that gives an exponential decay rate. And when we integrate this, is the exponent minus gamma time. Now, suppose we have just one particle, which means that n0 is 1. Then this expression should be treated as the probability of survival of the particle, the probability that the particle survives by a given moment of time. So in the case of one particle, we can write as P equals exponent minus gamma t. So if you know that particle exists in the moment of time t equals 0, then this gives you the probability that we still find this particle undecayed in the moment of time t. Okay? So this is the probability, and the probability is given by moduli square of wave function. So now we are talking here about presence of particle in space-time, right? So which is in the usual configuration space. And the probability in quantum mechanics is given by moduli square of the amplitude or wave function in configuration space. So this is wave function in configuration space. So let us reconstruct this psi, knowing what is P. So how you would write x this way, the wave function, knowing that that probability is given by expression with this exponent. So what you would write?
That over 2.
Yeah, so let me write this minus 1/2 gamma t.
E to the I minus in the energy.
In general, it's k, right? X. So when you compute moduli square, this disappears, right? But that corresponds to plane wave. So we are considering isolated particle, and therefore it can be described by this plane wave. So let us consider this in the rest frame, and then psi can be written as I introduce E0 here, time minus 1/2 gamma time. So this is the wave function of decaying particle in configuration space. So now let us find this wave function in the energy momentum space. So what we are doing for this, so I want to find psi E, and for this we need to do Fourier transformation, right? So we take this wave function in X space and do Fourier transformation. This means that this psi E is given by dt exponent I energy t, and then psi t. So which can be written as the integral, and I will take integral from 0 when I say that this is my initial state for my, that I know that particle exists, to infinity dt exponent I e minus I0 time minus 1/2 gamma time. Okay? So the integration is trivial. And let me give you final result. It will be 1 I okay, so what I'm doing, I'm just having this, combining these two terms with t, and then do redefinition of variables, and therefore this combination will go in denominator, and then make integration from 0 to infinity. Okay, so no need to do problem with this explicit. So this was what I'm getting. Now the probability to find decaying particle with energy E is given to moduli by moduli square over this E. And this is moduli square of this expression, which is square, and this is plus 1 to the 4th gamma square. Just moduli square of this formula. Right? So let me just draw this dependence. And this dependence has the form of peak. With maximum at A0, and the width on the half of the height is given by gamma. Right? So this is gamma. So this is actually why we call also this decay rate as width of the resonance. So it gives you the width of this resonance form. And this is nothing but Breit-Wigner formula, right? Breit-Wigner peak. Let me remind that we obtain this peak starting from exponential decay low in configuration space. So I have this probability as a function of t, and exponential law of decay in configuration space corresponds to the peak in the energy space. Okay?
Here is P in the y-axis.
Oh, sorry, yeah, sure, it should be P. Because, thank you. So what is the meaning of this resonance? The meaning is that if you have decaying particle, it has no definite energy, right? So which means that doing measurement of energy of decaying particle, you can find with some probability the energy here or there. Okay? So. So we have distribution in energies. And this actually reflects uncertainty principle, because if you have decaying particle, there is uncertainty in the fact when it decays. We don't know a priori, right? So it may decay now immediately, it can decay after some time, and the lifetime is tau. If the lifetime is tau, it can decay in the moment of time t, or 10t, or 20t, or whatever it is. So there is, of course, probability here. There is uncertainty in time. And this uncertainty in energy precisely reflects uncertainty in time. Now here we have central values of the energy of maximum, which is A0. And if we are in a rest frame, so then this is a mass. And therefore we can say the decaying particle has no definite mass. There is uncertainty in mass. And what we call really the mass is this maximum value of this peak. So we can write instead of energy the mass, and here it will be m0. So and usually what we call the mass of decaying particle is this position of maximum. Sorry. And again, making measurements of mass of decaying particle, in different measurements we will get different values of this mass. So it will be distribution in the mass. So the fantastic measurement is the measurement of Z0 mass. And so this kind of curve is actually measured with very high accuracy. I think if someone was at the Peskin talk, he showed this very precise measure Z0 width. Okay, so what else? And so this peak is actually origin of the peaks which we have seen when we discussed a discovery of J psi and also epsilon. Okay, so that's the origin of the peaks when particle is produced. Then we observe the peak and the probability. Okay. Now, before I will start to discuss description of resonances in quantum field theory. Also, you don't know quantum field theory, but nevertheless, I will describe how it is done. But before this, I need to introduce one important thing. So what I will introduce now is optical theorem. Who knows what is the optical theory? Oh, okay, good. So, anyway. But probably you don't know what is relation to resonances. Oh, you know? So, optical theorem. Optical theorem is the consequence of unitarity of S matrix. So we consider the process when we have some number of particles in initial state which approach each other, interact in interaction region, and then we have a set of the particles in the final state, which we describe as a plane wave. So we are considering that these particles are at infinity, they are no more interacting between each other, so they're just free propagating particles. So this is the standard scattering problem. So we introduce S operator, which is responsible for transition between an initial state and a final state. So let me also introduce the total momentum of particles in initial state and total momentum for momentum of particles in final state. So we introduce this S operator and introduce S matrix as matrix element between final and initial states of this operator. Okay, so this is how we introduce matrix. And so then we need to have all these possible initial and final states, and we have this matrix. Okay, so unitarity of this S matrix means that S dagger S is unity matrix, which actually reflects just conservation of probability. So if you have a given state I, then the total probability that it can be transformed in any final state is 1, right? So you have no disappearance of a system. So that actually reflected by unitarity. Now, let me present this S matrix in the following form. So I will be quite sketchy, and I will ask you to do as a homework to repeat these simple computations. So what I can do, I can put out delta Fi, which corresponds to the situation when there is no interaction, and so you have the same initial and final state. So I'm interested still in some transitions, right? Then I will introduce invariant amplitude in the following way. I 2 pi to the 4th, then delta function pi final minus pi initial multiplied, so I'm continuing, multiplied by product of 1 square root of 2 energies J, and these are energies of external particles, all in initial and final states. So J counts all the particles in initial and final state. This is just normalization fact. I'm normalizing my wave functions in such a way, in such a way that I have this square root of 2 energies. It corresponds to 1 particle in unit volume. Now, then other factors. Well, actually, that's it, right? And then I have this Fi. Which is called invariant amplitude. Okay, and I know how this MFI determines cross sections of probabilities. So I represent my S in this form. And then I insert this in the unitarity condition. And let me give you result, and I explain, and I will ask you to check this. So I have unitarity condition, which I can write this in the form N S F N times S N I dagger, and this is delta Fi. So SS dagger can be written explicitly in this way, and here I make summation of all possible intermediate states. Okay. So what I'm doing, I'm inserting expression for S in terms of invariant amplitude, and then what I will get is the following: product 1 over two energies. And I make another step. So I insert, so I insert this expression S and S, and put I equals F. The same initial and final state. Okay, so what I will get is following. There will be imaginary part of MII equals 2 pi. I think for the force square. It should be pi to the force, yeah. Pi to the 4. And the sum over n over n reduced m I r moduli square and delta function pf minus pi. So this is what I will get. So let me just give you some hint how you can get this. But I will ask you just to check, insert, and there's no big problem with this. So you have two terms here, right? So that's continuation. Right? Two terms. When I insert here, I will have 4 terms, right? Product of 2 terms. The first one is delta times delta, which actually cancels with this one. Then 2 terms are left, 3 terms are left. 2 of them are cross terms when I multiply this by that, right? And conjugate. And that gives me, because of this I, imaginary part of the amplitude MII. Okay? And this is what comes from square of this second term. So please do this check. Nothing special. The expression is very important. So, by the way, here I just making change notation, not to confuse with n, because I'm using here instead of n, I'm using this r. So this is summation of over all possible states to which I can be transformed, which includes the states with different momenta, with different number of final particles, everything. Can be 2 particles, 3 particles, 5 particles, and also with different momenta, so that this sum actually is both the sum and integration. So everything, so all possible degrees of freedom should be integrated or summed. Then it's exact expression.
So it is related to the total cross section.
So wait a minute.
Okay.
We'll come to this. So the key point is, and this is optical theorem. So this relation is called optical theorem. So that has been obtained first with in optics, and then this type of the expressions, and then generalized to particle physics situations. So what we have here is connection between imaginary part of the amplitude of forward elastic scattering. So initial and final, yeah?
The delta function, shouldn't it be like pi instead of pi?
Yeah, so let me check, because I made some shortening. It should be p r, yes, I think. Yeah, it should be. So from this equation I have a relation of imaginary part of the amplitude. I made some shortening in this because so some coefficient it is related to the sum over this r p n This is coefficient. With these pi's and the energy. This is imaginary part important. Which is part of elastic forward scattering of amplitude of elastic process. So when I go to the same state, and this is total probability, right? It's total probability important. Of transition of state I into everything.
Shouldn't that be R?
Yeah. Okay. So this is optical theorem, and it has quite simple graphic representation. On the left-hand side, we have imaginary part of the process of the type when we have some initial state, which is transformed to the same state in the end. And this is K multiplied by the following. We have state I, which is transformed to everything. And then we take moduli square. This is R. And this can be written. So now, okay, let me do this. So we can kind of cross this. And what is staying here is we have this, and then multiply by conjugate, which corresponds to the process of this type. So it's I, and here is our R and our state. And this we can just write like this. So this type of derivation is not accidental, right? So the only non-trivial thing that I should take imaginary part here. Questions?
And this theorem also gives rise to something known as cutting rules, Feynman diagrams, where we can extract the imaginary.
Yeah, so you can you can use this actually for computations. If you want to compute total cross section, for instance, you can do this this cut of the. But I don't want to discuss this in detail. Now let me finish this lecture by applications, and there are a few applications depending on what is initial state, what is state I. Suppose I state is composed just from single particle, A. Then imaginary part, we need to compute imaginary part of the following process when we have A. And in final state, we again have A. And that should be equal to, with some coefficient of the process when we have a single particle, which then transform into any particles. It can transform moduli squared. What is this? This is nothing but decay rate, total decay rate. Actually, what you see here is what we call polarization operator for photons. So, in the case of one particle, optical theorem is reduced to the following relation between P, and so this is what we call S square root of S and gamma A. And this comes from all these kinematical factors, this 1 over 2 energies. I don't want to, you can do this derivation. So we have connection between imaginary part of polarization operator and decay rate, total decay rate. So what's important? That's total decay rate, not for some specific channel. And now, of course, if we have two particles, so the process of this type, then this can be connected to total cross-section of interactions of two particles. But I will mostly use this. So here I have connection to total cross-section. So here is decay rate, and here I will have a connection to total cross-section. So we have A, B, A and B. So this process. Then I can connect imaginary part of this process with the total cross-section. Which is this, and then moduli square. Okay. So, by the way, if Giovanni introduced propagators of particles, do you know what are?
Yeah.
He introduced already, right? Fourier functions. Okay, good. So, there is no more questions.
Recording.
Hmm?
Recording.